Hello everyone. In this presentation, I will introduce our work, Learning Tiny Models by Raster-Scanning Images. In recent years, there has been a growing interest in expanding the scope of Edge ML to the ultra-low power systems, called TinyML. To perform various always-on use cases, TinyML typically operates in the milliwatt range, powered by general-purpose microcontroller units or application-specific integrated circuits. Due to the power constraints, TinyML suffers from a hard limit on the memory size. This is because more memory consumes more power. Typical microcontrollers can only have memory up to 300 kilobytes, which is about 6,000 times smaller than the mobile constraints. Using conventional CNNs for TinyML is challenging, since the runtime peak memory explodes in the lower layer of the network, regardless of how small the model size is. Therefore, a common solution is to reduce the input resolution at the cost of accuracy. To tackle this problem, we recall the Raster-Scan-based processing in image sensors. The sequential processing is beneficial as it requires the buffer only for the current scan line. From this motivation, we propose a Raster-Scan-based neural network for low-power systems. First, we divide an image into a group of T raster-scan sub-images with only height reduced to K. Then, we read T sub-images sequentially using a multi-head CNN to output a feature map of height 1. Next, RNN is used to capture the vertical context for image level classification. The current raster-scanned feature FT is used to update the hidden state of RNN. For implementation, we use a variant of GRU which adopts 1D convolutions rather than fully connected layers. To be specific, for each pixel location, we process a shared RNN using 1D convolution. Because RNN is shared across pixels, our convolutional RNN holds both vertical and horizontal invariance. In addition, there are also an attention module and confidence loss that exploits the proposed raster-scanned architecture. Please refer to our paper for more detail. This is the overall architecture of our method. After scanning reaches the bottom of an image, we use the last RNN hidden state for an image level classification. Looking at the class activation map of RNN, the heatmaps start to be salient when the uppermost parts of the targets are raster scanned and is maintained until it reaches the bottom of an image. This is because the information is carried all the way to the last scan line, where the final classification is performed. Also, we introduce an early termination scheme based on the confidence score of the current scan line. Because it does not require to process a full image, the number of operations reduced by 35% for positive images. In the right figure, we can see that scanning up to the frontal face is often enough for classifying a person. We compare our approach with other tiny models on the VWW dataset. VWW solves the binary classification task given the resource constraint of TinyML. Our method advances the Pareto optimal frontier using 24.3 times smaller peak memory and 12.9 times smaller weight memory with competitive accuracy. It also shows better computation efficiency by adopting an early termination, which is shown as a dotted blue line in the rightmost figure. In summary, we propose a Raster-Scan-based architecture for ultra-low power systems. RaScaNet achieves state-of-the-art Pareto efficiency, operating within 60 kilobytes in total memory usage. We hope that the proposed method can bring deep learning closer to image sensors. This is the end of our presentation. Thank you for listening.